Video, speaker, good. All right, and we're recording, good. Technical errors. So we're going to start our new human body systems. I saw when I checked tests last night, I saw that about half of you had already finished them. So maybe some of you have finished it since then or did it this morning or whatever. So anyway, that's good. And we'll be looking forward to wrapping up Q3, right? Wrap it up, get into fourth quarter, we're almost done. Summer's coming. Everybody ready yet? I don't really want the heat, but I'll take the time off. So we are doing digestive and excretory. Your book didn't cover excretory too much. So we're going to cover it a little bit today. And what we're trying to do, again, is we're trying to keep your lessons aligned with the other classes' lessons so that we can have labs that are cohesive and coherent and make sense. So we're going to be starting today with you guys talking about food and nutrition. And our lab is really short, so we're actually going to play a little game. I'm going to grab some random food packaging from around the house, and then everybody's going to guess, you know, which has the highest calories, which has the highest carbs, which has the highest proteins, fats, just to see how we do. Will be interesting. So we're talking about calories. When you hear about calories, what's sorry, I'll put this on top of it. Mess it up. So what's a calorie? Does anybody know what a calorie is? Do we know? How about those of you who did chemistry or physical science? So calorie is a unit of energy or heat, but it's the amount of heat or energy that's required to raise 1 gram of water, 1 degree Celsius, if you're measuring this all at 1 atmospheric pressure. So that means basically at sea level, not below sea level, not above sea level. If you took 1 gram, which is also 1 cc, 1 cubic centimeter of water, and you used enough energy to make it go from whatever, 32 degrees, or not say 32, that's, we're thinking about Fahrenheit there. I'll say 70 degrees Celsius to 71 degrees Celsius, you used 1 calorie worth of energy. But when we talk about food, we're talking about calories, we're actually talking about kilocalories. So we use this word differently in nutrition. We're talking nutrition science than we do when we're talking like chemistry or usually biology or physical science. So a calorie is, in nutritional terms, is actually a kilocalorie. It's 1,000 calories. But for whatever reason, we don't use that prefix when we're talking about it in terms of food. So if you see a, say you see, okay, well, this is an example. So this says it's 50 calories. So how many calories is it really?
It's
if it says
how many?
1,500. Other way around. So if this says it's 50, not quite. So if we say when we say calorie, we're talking about food. We mean kilocalorie, which is 1,000 calories. So if this says 50 calories,
5,000.
not 5,000.
50?
50 what?
50,000.
You get a coin. Drew's coin. Ah, see how this works? Okay. So there's really 50,000 calories in that. Now, if it said 50,000 calories on that, no one would drink it because everyone would be thinking that's a crazy idea, right? So really, when we're talking about food, though, we don't even abbreviate it kilocalorie. So here are some ideas or some examples of how much energy you have to expend to burn those calories. So basically, you are an endotherm, right? What is an endotherm?
So it makes its own.
That's 2 for you. Okay, look at that. The hand went up and I answered it. Okay, so an endotherm we make our own heat. What's the process we're using to make the heat? Anybody beside Drew know? What's the process your body is going through that's producing heat?
Like respiratory?
You're very close. Think on it. It's a chemical equation you've seen before. Claire, were you gonna say something?
Circulatory?
No? You were.
It's like photosynthesis or the other one.
What's the opposite of photosynthesis? You were really close before. Okay, so cellular respiration, right? Which is the opposite of photosynthesis. Remember with photosynthesis, what do plants breathe in?
Carbon dioxide.
Hey, Claire gets one. Okay, so carbon dioxide, right? Plants it. So it's CO2 plus H2O plus sunlight. There's your energy. And you get from it sugar, C6H12O6, water, right? And then when you do it the other way around, the energy gets produced rather than taken in. So you take your C6H12O6, your sugar, and you take your oxygen. Oh, that was the other thing. That's the other waste product in photosynthesis. So your sugar and your oxygen, and you're going to produce heat and carbon dioxide, right? So and water. So that heat that you're giving off is part of your cellular respiration process. So you're using a sugar, right? When you do that, that's part of your process is you need a sugar to break down in order to undergo cellular respiration. So it's when this sugar, that's where the calories are maintained within the sugar, right? That's where the unit of heat is. That's the energy, and it releases heat. So basically you have stored energy in sugar and you're changing it to heat energy when you go through cellular respiration, okay? So if you drink a sugary soft drink, it's 138 calories, which means it's 138,000 calories if we're being accurate, right? And in order to burn that off, so here's what it says. It takes time to burn off calories in minutes. So walking 3 to 5 miles or running 5 miles. So if you're going to drink this soft drink and it's going to take you 26 walking, 26 walking at 3 to 5 miles per hour, running at 5 miles per hour. So if you go walking, it's going to take you 26 minutes or 13 if you're running to burn off one soda. Does that make sense? And if you're going to eat this, I think that's a Snickers, don't you? I think they're trying to not get in trouble for sticking the word Snickers on there, but I'm pretty sure. So 229,000 calories, you're going to burn those in how many minutes of walking? 42 or 22 of running. So what's the most high calorie item on this page here?
Sandwich.
The sandwich. Okay, so why do you think the sandwich has so many calories compared to the other things? Does anybody have an idea? Anybody besides Drew? Drew, what's your idea?
It has lots of different stuff on it.
It has lots of different things in it. And okay, so bread is carbs, right? And carbs break down into sugars. So that's a lot of it. Now, obviously, there's a lot of sugar in here because this is also carb. It breaks down into sugar, plus there's sugar in it. But there's also all kinds of other things in here. It's much bigger than a blueberry muffin. So that's partly what's going on there. So you also burn so you're sitting right now, right? You're not doing anything. You're just kind of chilling. You're burning calories just sitting because your body's going through all of its normal metabolic processes. But when you're sleeping, you're burning even more than you are when you're just sitting still. Why do you think that is? What happens when you're sleeping?
I lose 3 pounds every time I go to sleep.
Yeah, Drew swears he loses 3 pounds every time he goes to sleep because he weighs himself at night and in the morning. He's like, where did it all go? So what do you guys think? Why do you think you might burn so many calories when you're sleeping?
Because
Claire's answering.
Because you're working harder when you're sleeping,
Yeah, what's your body working on?
keeping you alive.
It's doing that. Yeah, I'll give you a coin for that. So yeah, basically that's when your body starts repairing things. Your body's doing all this cellular repair. It's getting rid of, it does it all day long, but at night, it really, when you're sleeping, it concentrates on that stuff. All right, so food. So our molecules in food contain chemical energy that cells use to produce ATP. Remember ATP? That's our little energy source. Food also supplies the raw materials your body needs to build and repair tissues. So the following nutrients are necessary. This is what we call nutrients. So typically we say there are these 6, and sometimes people add fiber. Now, fiber isn't needed in the way this is defined. So here it's saying that you're breaking down, that you need the chemical energy. You need the chemicals in order to have chemical energy, and then you need the other raw materials to build and repair. But without fiber, your body would not be able to get rid of waste. And without getting rid of waste, you would become toxic and you would die. So you do need fiber, but you're using it in a different way than you're using these other nutrients. These are all used for energy and building. So it's a little different, but it's one of these things you do need in your diet. And most of us do not get enough of it. Because if we were not living in our, civilized modern world with our houses and all this kind of stuff, if we were actually, foraging like our ancestors did, and we were living outside and we had to go and go out into the woods and find things to eat or plant our own gardens or whatever, we'd be eating a lot more vegetables than we do and fruit than we typically do. We eat a lot of processed stuff, right? Today, it's easy. I do it all the time. Grab a granola bar. It's so easy. But if we were actually having to go through the process of finding our own food and whatnot, we'd probably eat a lot more fruit and vegetables. And in that case, we'd have more fiber. So that's something we should really look at today as humans. So carbs, everybody hears about carbs, right? Carbohydrate is an organic compound such as a sugar or a starch that is used to store energy. So a sugar by itself is one thing. A carbohydrate is like a bunch of sugars stuck together. Do you remember when we look back at that? Way back in first quarter, I think is when we talked about carbohydrates and energy and things like that. So most organic compounds, carbohydrates are built of small repeating units that form bonds with each other to make a larger molecule. In the case of carbs, the small repeating units are called monosaccharides. Well, there's saccharide right there is sugar. What's mono?
One.
Oh, Claire. One. So you got one sugar. So you have one sugar and then it repeats. And that's how you get a carbohydrate. So remember, it has carbon in it. And then the hydrate part is because it also has water in the molecule. So here's some examples of carbs. Now you may hear people say, I don't eat carbs. Well, everybody eats carbs. They're eating low carbs. These are like the same people that say, I don't eat sugar. I know people who say that, I don't eat sugar. Yeah, you do, or you be dead. You have to have sugar. It's required. It's required for your body to function. What they mean is, I don't eat refined sugar. I don't take table sugar and put it in my tea. That's what they mean. Everybody eats sugar. Everybody eats carbs, but you can't eat a lower carb diet. And probably most Americans should eat smaller amounts of carbs than we do eat. We eat a lot of carbs. We eat a lot of bread and stuff like that, pasta, because we love it. But so your carbs are your big energy source. And this is why we have to watch how much we eat. Because if you eat too many carbs, you're putting in a lot of fuel for energy. And if you're not expending that energy, your body's going to take all that leftover energy and convert it to stored energy, which is fat in your body. It's going to take it and go, well, we're not using it now because your body doesn't know. Here's the thing. Your body doesn't know that a mile and a half away is a Publix. It has no idea. So if you eat a whole big giant bowl of mac and cheese and then you sit on your butt for the remainder of the day, all your body is doing is going, my goodness, we're not using this energy now, but tomorrow there may be no food. What if there's no food? So it turns it into fat so that you have something to eat off of in case all your food disappears, because your body doesn't know about Publix. You do, but your body doesn't, which is why you have to be smart when you're shopping. So you have your starchy stuff, your potatoes, your bread, your rice, and pulses is like some other kind of grain. I'm not even sure what they're doing there. And then you have sugars. You got natural sugar like fructose. People who say they don't eat sugar, eat fruit all the time. I see them do it. Yep. So there's tons of sugar in an orange. That's why if you have a diabetic person, sometimes just drinking a little orange juice can fix it. Or if you see people who go and give blood, they usually give them orange juice and stuff when they're done giving blood because it puts sugar back into your system. Table sugar, honey, of course, is full of sugar. Milk, lactose is the sugar in milk. Our lab today is going to involve working with lactose in particular, which is milk sugar. Some people are lactose intolerant, huh? Yeah. Some people are lactose intolerant. They don't do well with milks is basically, yep. And then this says biscuit. So that tells you this is British, probably, this picture, because we don't call these biscuits, we call them cookies, right? But if you're in the UK, they call it a biscuit. But to us, a biscuit is something totally different. A biscuit, looks like a biscuit, right? I mean, Southerners, we know what our biscuits are. You don't mess with biscuits, but they call these biscuits, which is particularly humorous. So, and then unsweetened juice is still going to have sugar, just a little less.
Why does the honey look like an egg?
I don't know. It does kind of though, doesn't it? So fats are a type of lipid consisting of triesters of glycol, fatty acids, and triglycerides. So basically these are just the types of smaller molecules that make up a long chain lipid for a fat. So because they're organic compounds consisting of carbon and hydrogen atoms, they are generally soluble in organic solvents and largely insoluble in water. What's soluble mean? Who knows? Somebody that's not Drew know what insoluble means? Or soluble? So soluble, we did this way back at the beginning too, and this is another good chemistry term. Soluble means able to be dissolved. Remember, we have the solvent and the solute. If the solute is soluble, it will dissolve in the solvent, okay? So, or these fats and stuff, they are generally soluble in certain organic compounds, but not in water. If you pour oil on water, does it mix? No, because it's not soluble. Oil will not dissolve in water.
Is that also because it's less dense?
It'll float because it's less dense. That's right. So fats help the body absorb fat-soluble vitamins, which are part of cell membranes, nerves, and contain certain hormones. So we have certain hormones that have to dissolve in fat. These are the ones that you see sometimes people have to inject them into, like diabetics and stuff will inject into insulin into their belly fat because it's a fat-soluble hormone. And then you'll have things like cell membranes. They have lipids in them, right? We talked about how there's this lipid bilayer, that phospholipid bilayer that allows things in and out of cell membranes. You have to have your lipids for that. So you have to have some fats. So the people that say they don't eat fats, they're lying too. They're eating fats. They just may not be eating as many fats, right? Fats come into everything. And there are different kinds of fats. There's saturated, unsaturated, trans fats, mono, poly fats.
Would an increased amount of like testosterone cause you to burn more calories?
No, not really. But if you're getting increased testosterone in a natural way, like your own body is putting it out, it probably is also putting out other, it's also going through other changes that would need you to consume more calories, basically, because you'd be growing usually when that happens. But like if you get testosterone injections, it's not really gonna, it's more like the need to eat more calories is going to be a byproduct of the testosterone rather than the other way around. Does that make sense?
Yeah.
So there are some fats that are, they call good and bad. So you can get really good fats from things like almonds and avocados. That's much better for you than the fat you're going to get from these trans fat things. These are usually our processed stuff, right? I had a friend I used to work with who would read every label, and if it had trans fats in it, he would just put it down. He's like, I'm not eating that. He was really anti-trans fat. So proteins, we remember what proteins are, right? They're composed of amino acids. What are amino acids? Who remembers?
The building blocks of something.
Of what?
Proteins.
You were going to say it. Proteins. Okay. Building blocks of proteins. I'm going to give 3. You get one.
Proteins are made of amino acids.
You get one.
Amino acids are made out of what?
They're the building blocks of proteins. Now, what are amino acids made of? Who remembers what amino acids are made of? Amino acids are the building blocks of proteins. What?
Atoms.
Well, everything's made of atoms, but what? Do you remember? So this has to do, if you remember all the way back to DNA and RNA, when they code, you get those little nucleotide bases. And you remember they code for those little codons, and they spit the little codons out, AUG, that kind of thing. And those together will form an amino acid, and then those form a protein. And they're joined by peptide bonds. So proteins supply raw material for growth and repair. This is necessary for stuff. And you have different kinds of proteins. You have complete proteins. That means they have all of your 9 essential amino acids. Now there's like 30 some amino acids, but there are 9 that we call essential. You got to get them from someplace. These are the ones you have to get from someplace. Your body's not making them. You got to get them. And then we have incomplete. So this means they're missing some. So this is why people who are vegetarians or vegans, but vegetarians and vegans in particular, have to be very careful about what proteins they consume, because these main products that we consider protein products are animal products, right? So if you look over, because obviously we're the ones that are we're making proteins, like plants are doing it too, but we're making more. So if you are a vegetarian, you are going to need to eat certain combinations of these things throughout the day to equal one of the things from this side of the chart. So that's why you may see like a vegetarian can't just replace their like meat with beans and move on. They have to do beans and something else. That's the way to be sure that they get all their protein. So vitamins are any group of compounds, organic compounds, which are essential for growth and nutrition, required in small quantities in diet because they cannot be synthesized by the body. We don't make these. Now, the point about vitamins is that they're organic compounds. So they're not minerals. Minerals and vitamins are both needed by the body. They're both things we don't make, but minerals are going to be actual elements. They tend to be things like metals. We take in a lot of metals that are necessary. Some metals are bad for you. Some metals are good for you. So most vitamins are needed by the body. Huh? Yeah, that lead's not good. So guys, watch the volume, please.
Mercury.
Yeah, that's not good. So most vitamins are needed to help perform chemical reactions. So here are examples of some of the vitamins we take in every day. You know, you can see here's your potassium. We call this vitamin E, D, C. They aren't necessarily named. This is not like a periodic chart. Okay, so these are not named necessarily for the types of minerals that are in them or types of elements that are in them. But K in particular this one is, it does involve potassium. So when you look here, you can see like B12, B9. You see these when you look at the back of nutrition labels sometimes? Yeah, that's what these are. So you need these in order to perform chemical reactions in your body because they're going to contain other parts of other elements of that reaction. So here's where your minerals are. So these are inorganic. That's the difference. Vitamins are organic, minerals are inorganic. And you have to have these to function naturally. So only in small amounts. These in particular are exactly straight off your periodic table. So what's this one? Ca.
Isn't that potassium or something?
Not potassium, calcium. What's Cl? Chlorine. What's Cu? Copper. You need copper. You actually do. You need it in small amounts. How about Fe? Iron. Yeah, another coin. Here's how you get coins. I can't give you that one. It's not American. Won't go in the machine. How about I? Iodine. You need iodine in small amounts. What's K? Potassium. Mg is magnesium and Mn is manganese. Now this one's an easy one. You should know this one. What's Na? No, what's Na? You know it.
Is it metal?
What is it? It's sodium. Okay, sodium. What's P? Do you remember? Phosphorus. Se is selenium. That one's harder. How about Zn? Zinc. Yes, that's what these are. So you need these in order to get through your day. You need them. They're in all kinds of things that you eat. So water, of course, you need water to survive. Every cell, tissue, organ in your body needs water. And for example, your body uses water to maintain temperature, remove waste, lubricate your joints, overall good health. So here's some ways that you use water. Mucous membranes, eyes, mouth. Obviously, these are wet parts of your body that you're aware of, right? 3/4 of your total body mass is water. And let's see, maintains optimal digestive function and elimination. If you don't drink enough water, you will get constipated. Not fun. You have to drink a lot. And that's especially true if you're doing something where you're expending a lot of energy and losing a lot of water through sweat and respiration. Like if you're working out, you have to drink a lot.
At summer camp, my whole cabin got dehydrated one night.
Mm-hmm.
It wasn't fun.
So permits the absorption of, oh, here's another thing to think about, elimination. This could also be that you're building up wastes within your body. So you build up waste materials within your body just by your normal metabolic functions. But if you're doing more of that, like say you're at your football match for the day or your gymnastics meet or your whatever, and you're working really, really, really hard all day, you're building up all of these waste products in your bloodstream, but you're not producing it. You're not drinking enough water to produce enough urine to get rid of it. This is why people get headaches when they're dehydrated. You've got stuff in your system that's not good. You're not getting enough good stuff where it needs to go because all the bad stuff's taking up space, basically. So sometimes if you have a headache and you don't know why, drinking water alone can fix it. So permits absorption of life essential nutrients and energy. Body can survive for weeks without food, but only a few days without water. That's very true. Maintains optimal, stable heating and cooling, facilitates blood flow, supports efficient removal of toxins. That's what we were just saying. Toxins is a loosely used term. Let me say that. You'll hear people, especially people that are kind of into like the whole, how do I say this? The sort of green, crunchy granola folks who sort of don't look at Western, they're not as strong on Western medicine as maybe some other people. So these people tend to use the word toxins a lot and they use it very loosely. But your body does have waste herbs. Well, yeah, your body does have waste products, right? And it does need to remove them. And if they build up, they can be toxic. But people will say, you'll hear it used throughout your life. Oh, do this and it'll get rid of the toxins in your body. Go sweat and it'll get rid of the toxins in your body. You have to think about that. Really think about it. Somebody once said, told me if you put castor oil on your feet and put on white socks and go to bed, it'll take all the toxins out of your body and you'll see it in the black in your socks. Well, the black in your socks is a chemical reaction from something else going on, but it does sometimes make black goopy stuff in your socks. That's not waste toxins coming. It's not like it's magically sucking all the waste from your body through your feet. If you think about like scientifically how these things work. So this is what percentage these particular organs are of water. So your blood is mostly water, 83%. Yep. And well, you got to think there's a lot of cells in your blood, and there's the other molecules that make up plasma. But if you look, like your liver is a ton of water, and so are your kidneys, which makes sense because they're filtering. Look how much water is in your brain. And look how much water is in your bones. Would you suspect that your bones were almost a quarter water? That's kind of weird when you think about it, because you think about them as being very solid, don't you? I do. I think of my bones as being pretty solid. But if you've ever taken a bone out of a piece of meat, like chicken or beef, before you cook it and compare it to one that's been dried, huge difference. Like you can feel it in the weight alone, between a dried bone and a fresh one. So here's your question. What percentage of the human body is made of water? Now, the exact answer we tend to use is also an estimate. So one of these is going to be closest. Which one do you all think it is?
80.
You think it's 80?
Yeah, I think 65.
You think it's 65? What do you think? 65? What do you think, Sky? You're going 65? How about you, Claire? Lily. What do you think?
What?
Which one of these do you think it is?
What?
Which one of these do you think is closest to the percentage of water in your body?
65.
65? Do you want to change your answer?
65.
Everybody says 65, and that's going to be right. We usually say 70. So everybody gets a coin. Yay, 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 yay. And there's Sky over here. All right, there we go. So everybody gets a coin. Yay. All right. So yes, 65 to 70, 60 to 75. We usually say 60, 70 is what people say, but that's going to depend. So now here's this. This is what we're going to do when we have extra time after lab. We're going to sit here and I'm going to look at these, and I'm going to see if you guys can figure out what's what, because it's going to be fun. So remember that when you're looking at this number, it's kilocalories, right? And these are important to read, because sometimes you're going to look here and see tons of calories, tons of fat, and very little vitamins, very little fiber. What you want to look for in most things is this number should be a little lower, unless you're trying to get energy, like you're about to go to a day of athletic event or something. So you're going to want your carbs to be a little lower, your fiber to be a little higher, your vitamins to be high, your calories to be a little low. And you want some of these fats, but you don't want too many. And you want some cholesterol, but not too much. And you definitely want to watch your sodium, especially if you're going to do something athletic. You're going to want a little more than if you're just going to sit around on your butt. And that's because sweating has salt in it. There's your sodium. So let's talk digestive system for a minute, because I'm watching our clock because we had a screwy morning. So your digestion is your process of breaking down food into smaller usable molecules. And it occurs in what we call our digestive tract, or our gastrointestinal tract, or alimentary canal, if you're talking about it from a developmental standpoint. And it's basically mouth to anus. Remember, alimentary canal was mouth to anus, and that's one of the first things that develops embryologically. And it's obviously super important, because without it, we wouldn't be here. So your phases of digestion include your ingestion, mechanical, chemical digestion, absorption, and then elimination. So when we talk about mechanical, there's two places really where the mechanical takes place. Where are they? Two main places in the digestive process where you get mechanical. What?
Chewing.
That's one.
And
Anybody know the other?
digestion.
Wait, what were you going to say? Stomach. Okay, so mouth and stomach. In your mouth. That one's yours. In your mouth. Oh, it's coming right back to me. Look at that. It doesn't want to go. So mostly you get your chewing in your mouth, right? Crunch, 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 crunch. That's mechanical. You're actually taking the food and you're breaking it down into smaller physical pieces, which increases your surface area and makes it easier for your body to break down more, chemically at least. If you're trying to dissolve, think of it this way. You're trying to dissolve a jawbreaker. You know those big jawbreaker chewy things? You don't want to chew them because they're trying to dissolve a jawbreaker in a glass of water, and you just stick it in the glass of water. It's going to be a long time. But if you crunch it up first and put it through your blender, or bang it with a hammer and put it in, you've increased that surface area, right? So it's going to dissolve faster. So that's the point. And then in your stomach actually moves and it churns and mixes your food around. It's like stirring. If you're trying to get that jawbreaker to dissolve, it's going to go faster if you stir, right? Same thing. And then your chemical is going to be also in your mouth. You're going to start to break down sugars in your mouth, which is why, for example, if you've seen diabetics that need they're getting low on their sugar, they can just put something in their mouth, and within like a minute or so, they're already feeling better, because it starts to break down the sugar of that, whatever that is, piece of candy or tablet or whatever they're taking. And then, so that'll break down in your mouth. And then you move to your stomach, where there's a little bit more breaking down, because you're putting in, that's where you got basically, you're breaking out the fat separately. And then you're also putting in acid from your body to start breaking things down more. So it starts to really begin it. And then as you move through your intestines is where you're going to start soaking up the nutrients. So you've got your mouth, your pharynx. Remember, your pharynx is between your back of your mouth and where your throat divides into your esophagus, which goes to your digestive system, and your where your lungs begin, right? So you've got these, it stops at this one point and breaks into two. And your pharynx is the combined area. So your mouth, pharynx, esophagus, which is the tube that goes basically from your pharynx to your stomach, small intestine, large intestine, and then rectum. So your mouth is mechanical, like we said, and then there's some chemical. Your epiglottis, okay, that's not this thing. This thing here is called a uvula. You can't see your epiglottis from your normal perspective. You'd have to go down with a little camera. But your epiglottis is like a little trap door. And basically, since you have one tube that is then diverting into air and food, right? You don't want air to go into your stomach, which happens, which is why you burp sometimes. Sometimes that's because you've, produced gases from a chemical breakdown and then they're coming up. But you swallow air when you eat. But you don't want to swallow a lot. That would be bad. That would hurt, actually. And then you also don't want food in your lungs. That would be really, really bad. So your little epiglottis is like a little flap, and it opens and closes and keeps things in and out places they're not supposed to be. So it closes off the trachea that lead into your lungs, basically. So when you swallow, like think about it, swallow whatever saliva is in your mouth. When you swallow, that little flap goes boop, and closes off your trachea so it doesn't go to your lungs. If you start choking because you've accidentally sucked in some saliva or whatever else, like you ever choke on your own spit? I've done it. It's so stupid, but that's what happens. That's like your little epiglottis failed you. So again, your epiglottis is way, way down in here, so you can't really see it. It's right here, but you can't see it. And if you look in the mirror, what you do see is this uvula. And some people want to think that's your epiglottis, and it's not. So your esophagus in your digestive system is almost 10 inches long. It's a pretty good size. And it secretes all kinds of mucusy stuff and helps things move, but it works through peristalsis. Okay, so hold your fist up like this. And whoever's next to you, I'll use Lily. You guys use each other. So shoot this like this, one on top of the other. All right, so if I open this one, because there's food coming in, right? You guys have to work together. If I open this one, there's food coming in. And if I close it, the next one's gonna open. So if I close this one, what's gonna happen with Lily's? Your top one's gonna open. Your top of this, yeah. And then when you close that one, your bottom of this is gonna open. So basically what you've got is this process where you've got a lot of food in here, it gets squeezed into that. And then it gets squeezed into this one. And then it gets squeezed into that one. And it's sort of like if you took a hose and you were working your hands down the hose to squeeze something through it or a tube, that's peristalsis. That's the process of moving. And that's why you can take a bite and then stand on your head. You can eat upside down. You ever tried to eat upside down or drink upside down? You can do it. Gravity isn't going to pull that stuff right back out. And it still hasn't made its way to your stomach. So it's still in your esophagus. So the reason it doesn't just fall back out is because you have these muscular contractions that are moving it along. Sometimes this stops functioning. And this is also the same process that works in your intestines too. Sometimes when this doesn't work, it can cause a really, really painful disorder. Sometimes it doesn't work because of a medicine, or sometimes people have just problems with this process, but it can be really, really painful actually. So if your acid in your stomach gets into your esophagus, it's called heartburn. And that's because you feel it up here, but it's really happening much lower in your body. And that's because there's actually a little sphincter muscle there, which is like a ring muscle that tightens. So when you've got that last bit squishes down into your stomach, that's supposed to seal off and stay sealed off. Sometimes this muscle gets weak for a number of reasons. If your stomach's overfull, for example, it can strain it, it'll open up, and then you get gastroesophageal reflux or acid that moves up into your esophagus, which is terrible, feels bad. So your stomach, I'm watching our clock, we're a little late here. Your stomach is this J-shaped thing. We talked about this, and it's going to break down food, right? Just break it down for the main part. Hydrochloric acid, that's what's in your stomach. If you throw up, it burns, right? Most of the time, it burns really bad. That's because there's hydrochloric acid in your stomach, and it is actually a very, very, very strong acid. Its pH is super low. We use it in lab all the time because it's such a strong acid. So if you're sick and you're throwing up and it burns a lot, you can always find like a Tums that has calcium in it that'll help neutralize that acid. You still might throw up and maybe it won't burn as much. Or like baking soda, which tastes terrible, but you could put baking soda in some water and it'll at least make it not burn so badly. So when your stomach mashes stuff up, it's called chyme. And this is how it all fits together. This is the guy that fails if you've got reflux, right? So we're gonna whip through these. Small intestine, this is where all your absorption is. It's 20 feet long, 20 feet long. So if you're about 5 foot tall like me, it's almost 4 times your height. No, I'm 5'2.5". But I'm saying if you're roughly 5 feet, 20 feet long is a lot. So that first picture that I showed you when I had the slideshow open, they have these little finger looking things. It's like hair called villi, and that's what's in your small intestine. That increases the surface area of your small intestine. And this is where most of your absorption of nutrients and minerals takes place. This is where your body sucks the good stuff out. And it's in 3 segments. It's a duodenum, which is the first part up in here, jejunum, and then the ileum is the last part. Sometimes people say duodenum or duodenum, either's appropriate. And so this is how these little guys work. See, all the surface areas increase. You got capillaries there, and it's sucking up all the good stuff and taking it through your bloodstream and putting it where it needs to go. So a lot of your water is taken up here, 80% of it. So what gets to your large intestine is much less watery. However, the final bit of water absorption occurs in your large intestine. This is where it sucks out, and this is 5 feet long. So it's probably about as long as most of you are tall. That's a lot. So there's a lot of surface area there too, and it absorbs the remaining water. And then the rest of it is what goes to your rectum to be stored up until it's released. So if you have, for example, if you're sick and you have diarrhea or whatever, it's probably because you're not absorbing enough of that water, and it goes shooting right out of you just like it came into you. So you know how that goes. Everybody knows how that goes, right? And your colon's made of 3 parts. It's got ascending, which means going up, transverse is going across, and descending going down. You also have right here on your ascending part. So here's your small intestines. Here's where your small intestine enters your large intestine. Whoop, whoop, come back. That guy right there is your appendix. It does nothing in you. In your ancestors, it did something. In some current animals, it does something. Anybody have an appendix? Who has an appendix? If you haven't had surgery, you have an appendix. I lost mine. You lost yours? Yeah. Yep. I lost mine a couple years ago. It was not fun, but could have been worse. So your large intestine is going to ferment, do a little additional protein breakdown, but mostly it's going to suck up the remaining water. And then you've got accessory organs, liver, gallbladder, pancreas. Your liver is going to produce the bile. Your gallbladder is going to store it till it needs it, squirts bile into your stomach. This is your emulsion process. It's basically like taking the fats and separating them from everything else, making it all into like a sort of a uniform mush that it's going to send through your body. And then your liver is going to do a lot of breakdown. Your liver is going to do some blood filtering. So are your kidneys. So these are necessary to get stuff you don't need out of your body. So both your liver and your kidneys are primarily for filtering. And your liver is going to break down your old red blood cells. Now, here's a question for you. Anybody know what color bile is? Bile. It's green. So it's actually green. So bile is produced in your liver. Your gallbladder stores it. It's actually green. Okay. Red blood cells are obviously what color? Red. What color do red and green make when they're mixed? Does anybody know? Brown. What color is your waist? There you are. Now you know why it's brown. In case you ever wondered, that's why. A lot of what you're pooping out is useless red blood cells that are of no good to you anymore. But they've been mixed in with everything else that's got bile, and that's green. So lastly, as we zip through here, your liver, let's see, it filters your blood, 1.4 liters per minute. That's a lot. There's your gallbladder. We found the gallbladder in both the pig and the frog, right? Remember the pig, it was really easy to see. Your liver's also right here, your pancreas, is going to produce insulin. And the important thing about that is that it's going to keep your blood sugar levels in check. You can't have too much, you can't have too little. Crazy little fun facts here. Intestines are 20, 25 feet, somewhere in there. If you were a horse, it would be 89 feet. And food passing through your large intestine can take anywhere from 18 hours to 2 days. This is why when people say, oh my gosh, I don't poop every day, I must have problems. No, sometimes it just takes longer. Your body is using more. If you eat a lot of junk your body doesn't eat, or you eat a lot of fiber, it's going to get through your body faster than if you eat a lot of protein. Like if you go through several days without any major fiber or carbs, you just eat meat all day, you're not going to poop a whole lot. You're just not. So in your lifetime, your digestive system handles 50 tons. 50 tons. So the excretory system, I'm going to put for you guys to look at later when you look at your, for next lesson or whatever, where to find these slideshows, but I want you to just look through it. There's not going to be a whole lot for you. The main thing you need to know is your kidneys are going to filter your blood, and they're going to send waste liquid, the liquid you no longer need, to your bladder, and your bladder is going to store it until you eliminate it. Somebody wrote all over these slides, which I found particularly funny, so I swiped them. So you also eliminate through skin when you sweat and through lungs when you breathe. This is how you get rid of waste in your body and obviously pooping. But your kidney's main function is to get rid of extra water and to filter your blood of things it doesn't need. So your kidneys are super important because without them, obviously, we'd have problems. And you can tell how important they are because they have so many blood vessels in them. So those are your units in your kidneys. I'll put all this up for you to see. This is stuff you're not expected to know. Like I said, the big things for you to know is your kidneys filter your blood, get rid of extra waste, and get rid of extra amounts of liquid. Dialysis, real quick. Do you ever see the little places that say dialysis? There's one right around the corner from here. You probably see it if you come from anywhere west or north of here. So dialysis is basically a mechanical kidney. It's a machine where they tap into one blood vessel, take your blood out, run it through a machine that acts like a kidney, and pump it back into your body. So I put shoes on so we can do lab. Run it back into your body through another tube. They take your blood out, they wash it, huh?
Do I need shoes for that?
No, you're fine. We're not doing anything that's going to break today, but I should have them because, you know, I am kind of supposed to be looking like somewhat professional person. So yeah, that's the purpose of your kidneys. So if your kidneys die or don't function well, you're going to end up with dialysis, which you don't want, because usually you have to do it like every couple of days. It's not something you do once. You have to go every couple of days. They tap in, run it through the machine to do what your kidneys do, put it back in. Not fun. So this will be available to you too. This is your start to finish digestive system. So we're gonna get ready for lab, and somebody can tell the other dudes that we're ready. And I'm going to put, let's see, we can end that. Okay, I'm gonna put this up for you guys so that you know where you're going. This can go away. Close this out. All right, so everybody's here except for Anthony and the Armstrongs